Good morning. Welcome to this lecture in the course on chemical engineering principles of CVD process. In the last lecture, we talked about CVD processes for depositing metals on surfaces. So, we talked about metal CVD using inorganic precursors as well as metal CVD using organic precursors, which is also known as MOCVD, metal organic CVD. And we just started discussing CVD of coatings. Coatings are a special category of CVD films because they have requirements that are different from other CVD films. Primarily, CVD films are very thin and they are put down on very critical submicron dimensional surfaces in order to provide certain functional properties such as conductivity or resistivity and so on. But CVD coatings are very different in the sense that they are much thicker. Typically, the coating must be of the order of microns rather than nanometers, and therefore, the conditions for CVD of coatings is very different from the conditions for CVD of other types of films. Now, when we talk about CVD processes for coatings, they are the same as any other CVD process. If you remember, in one of the first lectures, we described 3 or 4 methods of or types of reactions to make CVD films: decomposition, reduction, oxidation, and substitution / exchange reactions. So, the same types of reactions can also be used for CVD process, for CVD of coatings. For example, you can take a compound like NiCO4 and use that to deposit nickel solid plus 4CO. So, this is a decomposition CVD reaction to get a nickel coating. Another example of such a process could be if you want to actually make a tungsten coating, then you would, as we saw the other day, you can actually use either WF6 going to W plus F2, which is a decomposition reaction, or a WF6 plus SiH4, which can also lead to a tungsten deposition, or you can also do WF6 plus H2 going to W plus HF. Now, actually tungsten can be deposited therefore by all 3 types of reactions. This is a decomposition reaction, this is a reduction reaction, and this is essentially a substitution type of a reaction. And so, the CVD processes for coatings in terms of the types of reactions are no different from CVD for other films, but as I mentioned earlier, the primary difference is in the characteristics of the films that you are trying to obtain. They are much thicker and they have more emphasis on the physical properties rather than on their electrical or functional properties. And similarly, when you talk about designing a CVD reactor, the critical parameters are the same as for any other CVD system. So, the critical parameters would be the substrate temperature, the temperature distribution in the reactor, the operational pressure, the flow rates of the feed, the flow rate of the carrier gas, the flow rate of the reactant species, the concentrations of the reactant species, the reactor geometry, flow dynamics, and controls over the input, controls over the operating parameters, controls over the exhaust, and pre-treatment of product stream prior to venting into the atmosphere and so on. So again, the design principles for CVD reactors for coatings are essentially the same. So what makes CVD of coatings unique? What is really different about it? The primary difference again is the fact that there are some conflicting requirements on CVD coatings that have to be satisfied. They do have to be much thicker than a CVD film that we normally deposit. The problem is that as you make the coating thicker, adhesion or delamination issues become more and more difficult to deal with. When you have a substrate of some kind and you try to put down a coating on top of it, clearly for the most part the coating has a very different chemical composition and physical structure compared to the substrate that is underneath. That is the reason you put it down as a coating, right. But the problem with that is when you go from here to here, there is a very sharp transition in properties right at that interface. All of a sudden you get this huge change in chemical composition, in physical properties, in structure, in hardness, in density, virtually every imaginable parameter when you go from the coating layer to the substrate layer. And what that introduces is stress. So the biggest problem with CVD coatings is the buildup of stress at the interface between the coating and the substrate. If you can relieve the stress, adhesion will improve. Part of the reason why a CVD coating, or actually this applies to coatings that are put down by any other process as well, but especially CVD coatings, is that the film is ready to kind of detach from the substrate at the slightest excuse. So you have to provide an environment which will promote the adhesion of that coating layer to the substrate. So what are some of the techniques that are used for relieving the stress? The first is reducing thickness. Try to achieve your end effects with as thin a CVD coating as possible. The thicker the coating, the more the likelihood that it can disengage from the substrate, as well as if you have a thick coating, you can also have delamination within the layer itself. So one layer of the coating can actually detach from the next layer of the coating. So intra coating adhesion also can become an issue. So make the coating as thin as possible. The second is to increase the radius of curvature. Even though CVD is much better than other coating processes in terms of being able to follow the contours of a body, a smoother or more curved surface is easier to coat than one that has very sharp transition points. So you can make it easier for the coating to adhere to the surface by making the surface, by reducing the number of abrupt geometrical transitions in the body of the substrate. The third technique that you can use is to actually match the physical properties of the coating to those of the substrate. The closer they are, obviously the less will be the stress that is built up due to the transition. So particularly properties such as conductivity, thermal conductivity. Coefficient of thermal expansion is a very important one, because as the substrate coating goes through various cycles, what causes delamination to happen frequently is the difference in the coefficient of thermal expansion. So one of the most important parameters to try and match is CTE, coefficient of thermal expansion, particularly when the coatings are being used for high temperature environments. Now sometimes it may not be possible. You may have a metal substrate on which you are putting down a ceramic coating. You really cannot match the physical properties. Then a suggested method to handle that is, instead of having this very sharp transition where a property may suddenly drop like this to a much lower level or a much higher level, you provide a smoother transition. So, you provide certain intervening layers which will make the transition much smoother. So, instead of across the thickness of the film, instead of getting this sort of behavior, you try to smooth it out and get a more gradual transition. The way you do that is that in the CVD film, you deposit various layers with different compositions and physical properties. The layer that is closest to the substrate should most closely mimic the properties of the substrate, and then as you move away from the substrate, you can slowly start increasing the departure or the deviation of the properties from the substrate properties themselves. And so, this is frequently resorted to, again, to reduce the stress. The other thing that you can do to reduce stress is to essentially have the coating itself diffuse into the substrate. So, when you have these diffusional coatings, again it provides for a smoother transition. So, within the metal itself or the substrate, you will have a transition zone where the properties will change slowly from the properties of the coating to the properties of the metal. This also promotes adhesion, because once the coating material, coating element has actually penetrated into the substrate material, the interlocking is much stronger. So, it helps in both ways. It helps the mechanical interlocking between the coating and the substrate, and it also makes the gradient much shallower as you coat the substrate. So, these are all things that you can do, and of course, there is also the post processing, typically post baking. This is important to control the structure of the deposit, because it turns out that one of the major differences between a coating and the substrate is the morphology and structure of the coating and how that differs from the morphology and structure of the substrate. So, for example, if you are trying to do again let us say a metal coating on top of a semiconductor, the metal will have properties that the metal layer that you deposit, depending on the deposition conditions, can be a very amorphous structure, or it could have a more rigid structure to it. Now, in terms of stress, it turns out that in principle an amorphous structure should introduce less stress, because it is more accommodating as far as the stress distribution is concerned. I mean, you can imagine that if you have two very rigid bodies, getting them to stick together is more difficult than if you have one of the bodies being much less rigid than the other. It can actually deform in a sense, and therefore provide better adhesion and also more surface area for adhesion. When you have either two deformable surfaces in contact with each other, or one rigid surface and a deformable surface in contact with each other, the contact area, which is really what controls adhesion, is larger to begin with and tends to increase over time, because the two surfaces, as they contact each other, will continuously deform over time until they reach a steady state. So, what you will find is that the adhesion forces are actually at their lowest at time 0, and then with the passage of time, the adhesion forces will increase to a certain value and then they will stabilize. So, matching the structure is also important, and that can be done by post processing. For example, if you have an amorphous substrate and you are trying to bond an amorphous film, you probably do not require a post baking. However, if you have a substrate that is rigid and a film that is amorphous, that is okay for time 0 to get adhesion to happen, but then once the film is bonded to the surface, you want to control its structure to provide the necessary physical properties. So, you can resort to things like annealing in order to improve the properties of the CVD coating. Now, typically the properties that you look for in a CVD coating or things like rigidity, hardness, density, ability to withstand thermal cycling. Frequently these coatings are used in high temperature environments, but it is not just the high temperature, it is also the fact that the temperatures can frequently cycle between low and high, and it is really this thermal shock that can create damage rather than continuous exposure to either a high temperature or a low temperature environment. So, ability to survive in aggressive environments in general, whether it is high temperature or high pressure or highly reactive environments, that is one of the hallmarks of a good coating. Coatings also have to provide good resistance towards diffusion. They are frequently used as diffusion barrier coatings. So, this may be for a barrier against even water vapor diffusion if you are trying to protect something from moisture permeation, or it could be protection against diffusion of corrosive vapors or toxic vapors. So, diffusion barrier coatings are another widely applied usage of CVD coatings. And of course, classically erosion resistance and corrosion resistance have also been associated with coating materials. So, there are a variety of coatings that can be deposited for all these different purposes, and the CVD process again is sufficiently flexible that you can achieve virtually every one of these types of coatings using a CVD process. Actually, the history of CVD coatings goes back to the 1950s. The aerospace industry was actually the first one to use coatings as a diffusion barrier. It was developed back in the 1950s by the US aerospace industry, which by the way has been responsible for many innovations. People talk about clean rooms that are used for semiconductor manufacturing, but clean rooms were actually invented by the aerospace industry and to make rockets and space components. And similarly, they also invented CVD of coatings. The process that they used was something called pack cementation. So, this is in the aerospace applications. And again, most the application was diffusion barrier coatings in this case. Pack cementation is actually sort of a variation on a conventional commercial CVD process. What it refers to is, let us say that you have a metal on which you are trying to deposit some kind of a protective coating. In pack cementation, what you do is you take that reactive metal that you are trying to deposit and grind it into a powder, put it into essentially a vessel or a chamber in which the substrate is also located, the substrate on which you are trying to do the coating. Introduce a gas, an inert gas as a carrier gas, typically argon was used as the inert gas, and you also introduced appropriate reactive gases, typically HCl, H2 and so on. Now, and then you kind of pack all this into a container and you jack up the temperature to 1000 degree plus. So, what happens is that the reactive gases will flow through and they will react with the metals that you are trying to coat, and because of the elevated temperatures they will form the gas phase vapors of the metals. So, for example, if you have aluminum in the as the reactive metal, it will react with the chlorine in the HCl and it will form aluminum chloride, for example. The halides that you are forming will then flow over the substrate that you are trying to coat and they will deposit aluminum as a film, right. So, it is kind of everything is happening inside a vessel. Unlike the classical CVD process where the preparation of the precursor happens outside the CVD reactor and then you feed the precursors into the CVD reactor where the coating takes place, here everything takes place in one reactor, so to speak. You are generating the vapors in situ, and you control the transport phenomena inside this reactor in such a way that the reactive vapor species that are formed are directed to flow over the substrate that you are trying to coat, and the film deposition happens within the reactor itself. So, typically some of the coatings that are formed using this technique are aluminum, a process called aluminizing, boron, which is boronizing, carbon, carbiding, nitrogen, nitriding, and so on. The aerospace industry wanted to do it this way because essentially they do batch processes. I mean, they don't make a lot of components in a year. Unlike, for example, the semiconductor industry where they are trying to pump out 1 million wafers in a year. In aerospace, you may only make one of each in a year. So, you really need a good batch process that's well controlled, where you can take time, but make sure that you do it right. So, the primary disadvantage of this technique is that it is a batch process, it is slow, and it is not very energy efficient, but it will give you very repeatable and reproducible results because everything is kind of being done in one place. So, you can control that whole process very well. So, this pack cementation was invented back in the 50s, and then in the 60s the second commercial application of CVD coatings was for tools, tooling components, tool bits, because tools tend to wear easily. So, you need a coating to prevent wear and chipping of tools. You also need to reduce friction between sliding components, and there again you can use a coating to improve the frictional characteristics between mating surfaces. And the third problem is what is known as galling. Galling is where when you have two metals that are of somewhat comparable hardness and they slide on each other, they both tend to lose material and they actually tend to stick to each other because of deformation. As I was mentioning earlier, as two contacting surfaces deform, their contact area increases and therefore, they have a tendency to stick together. So, galling is a phenomenon that happens because of this wear of a surface, which then promotes sticking of two sliding components. So, all of these issues can be addressed by doing a CVD coating on top of the substrate. For example, if you have a tungsten tool bit, you can coat over it with tungsten carbide, or if you have a titanium tool, you can coat over that with titanium nitride. So, carbides, nitrides, and carbonitrides, TICN is another popular coating material for tools, and actually there is a fairly large variety of these types of coating materials. They all have increased hardness compared to the base material that they are trying to coat. So, for tools especially, the primary requirement for the coating that goes on top is that it should be significantly harder so that galling does not happen, but at the same time it should have good frictional characteristics and wear characteristics. So, there are some very specific functional properties that these coatings should have, and it turns out that a CVD process that is typically run as a low pressure hot wall CVD is typically employed to deposit these types of coatings on these substrates. Another application for the third commercial application for CVD of coatings was actually erosion prevention coatings. This became important when particularly in power plants where you are burning low quality fuels such as coal, you have a lot of these ash particles and other inorganic materials that survive the combustion process, which then get into the product gas stream and they start flowing over surfaces that are immersed. And as it happens, if you have sufficiently large particle that impacts the surface at a certain angle, you can have fairly severe erosion of the surface. So, you need to coat these materials with erosion preventive coatings. Now, these are usually ceramic coatings, alumina, silica, and again some of the carbide and nitride coatings have good properties for erosion mitigation. But in addition, you also need to have the same coatings need to also have thermal barrier properties, because again in power plants and also in gas turbines, the product gas stream can have temperatures in excess of 1500 degrees centigrade, because they have just come from a combustion process. So, depending on the temperatures that are obtained, particularly if it is an adiabatic process, combustion temperatures can be of the order of 2000 Kelvin. So, the coatings are not only need to be erosion resistant, but they also need to be able to withstand high temperatures and actually a fairly reactive environment, because of the high temperatures and the fact that you have a variety of inorganic and organic species in the gas stream. There will be a tendency for the combustion product gases to try and react with the surface, and so you have to essentially provide a chemically inert surface as well in order to resist any interaction of the vapors with the surface. So, the second and third applications for CVD coatings are tools and erosion protection coatings in power plants, boilers, turbine blades, etc. The fourth application, and which is probably the most important one, is corrosion protective coatings. In terms of potential value, this application far exceeds all the others, because it has been estimated that just in the US alone, the annual losses due to corrosion in various industries exceed something like $500 billion. So, corrosion protection in various environments is a very critical application. Now, in order for protection from corrosion, there are different strategies that you can use, and certainly coatings are a way to do it. But in this particular instance, a coating is not the smartest way to do it. The reason is that when you do when you talk about corrosion, the types of coatings that you can have are organic coatings, inorganic coatings and ceramic coatings, right. Organic coatings are typically biocompatible, environmentally friendly, but they do not survive high temperatures very well, and they do not survive chemically reactive environments very well. So, they do not really work when you are talking about particularly high temperature corrosion prevention. The second, inorganic coatings and ceramic coatings can provide the thermal resistance and the chemical resistance and so on, but they are expensive processes and they are not environmentally friendly. The processes that you have to use to put down these coatings can result in the discharge of very harmful chemicals, both in the liquid discharge as well as the vapor discharge. So, a preferred method is actually to put down a material on the surface, a very thin film of it, and allow it to again penetrate the top portion of the surface that you are trying to protect, so that just the surface that is exposed to the outside environment has certain properties that are superior to the bulk of the material. For example, again in gas turbines, the stators and the rotors are typically made of stainless steel. Now, stainless steel is good for most types of corrosion protection. However, stainless steel does not provide you with absolute protection, particularly at elevated temperatures and in highly reactive conditions. The primary reason is that stainless steel manufacturing introduces impurities, and it is these impurities that really initiate the corrosion and then it quickly spreads. So, even though you may have stainless steel as your substrate material, you have to provide additional protection to it, and especially if you start using the less expensive steel alloys, this becomes even more important. And in fact, if you look at the turbine industry in general, they do use steel alloys rather than stainless steel alloys in order to minimize the cost, but they have to immediately deal with corrosion. So, the lifetime of these steel components can be quite low. So, what you really have to do is use what are known as super alloys. So, these super alloys are also steel alloys, but with certain additives like chrome and nickel, which provide additional protection against corrosion as well as erosion, fouling, slagging and so on. The problem is these super alloys are extremely expensive. So, if you want to construct an entire turbine blade out of a super alloy, you are talking about 1,000 times increase in the cost of the turbine, which is not acceptable in order to get your process economics. So, what we do is use CVD instead and deposit the element that is going to give you that extra protection, such as chrome, nickel and so on, as a top layer on top of the steel substrate, and design the conditions to allow it to penetrate into the steel to a sufficient depth in order to provide the protection properties you need. So, essentially you are only turning the top layer of the steel into a super alloy. The rest of it can stay as a low cost commercial alloy material. So, it is kind of a smart way to achieve what you are looking for, because when you think about it, if your concern is mostly with surface exposure and surface phenomena, there is no point in trying to improve the material throughout the cross section. You only need the enhanced properties at the surface where the material is encountering the environment. So, it is a way of giving very localized protection. So, these corrosion protective coatings are typically metallic coatings, again iron, chrome and nickel are the most commonly employed metals in this application, and they are deposited as a thin surface layer, and they are allowed to diffuse into the substrate. Now, as we saw in the last class, when you are talking about CVD of metals, there are well established processes. There is metal CVD, there is MOCVD, which are very effective in depositing metal films on surfaces. The only problem is that typically again these work on small substrates, but in the case of turbines you are looking at very large surfaces that need to be coated. So, these techniques are not very appropriate for coating of large components such as turbine blades and so on. So, the process that is used in this case is one that blends some again a very classical chemical engineering process, which is fluid beds with CVD. So, it is called fluidized bed CVD, and the way this works is you prepare a bed of the coating material and fluidize it. So, you fluidize it again using a carrier gas that may be inert gas, or it could be hydrogen, or it could be nitrogen, and along with the carrier gas you also introduce certain reactive species such as chlorine or HCl or HF and so on, and then you essentially prepare this bed and you fluidize it using this mixture of carrier gas, inert gas and the reactive gases. And as this fluid passes over the bed with the metal particles will react with the corrosive gases and form halides. So, for example, Cr will form CrCl3, and then these gases, now the halides for example, are flown over the substrate that you are trying to coat. So, it could be a turbine blade, it could be a stator, it could be a boiler tube, whatever it is that you are trying to protect will be laid in the path of the product gases from this fluidized bed CVD, and as they encounter the substrate they will break down and deposit the metal on top of the substrate. Now, that is the first step. It allows you to deposit a layer on top of the substrate, but the key thing in doing corrosion protection using FBCVD is the second step, which is to provide sufficient time as well as conditions in order for interlayer diffusion to happen. You want the film not only to be at the surface, but it has to be subsurface as well. So, in any substrate you have essentially 3 layers. There is a bulk, the subsurface and the surface. So, the CVD coating has to be able to penetrate at least into the subsurface region, and you can actually control its depth of penetration by controlling things like time of exposure, the pressure. Essentially the higher the pressure, the more you can push the material into the substrate. So, by using a lower pressure you can reduce the depth of penetration, and you can also control it by turning on and off the reactant gases that are flowing in. So, as soon as you figure that you have sufficient protection or a sufficient thickness of this protective layer formed, you can turn off the flow of the reactive gases and prevent the film from forming. So, this process of FBCVD in combination with a post process can provide excellent control over corrosion protection of surfaces using a CVD process. So, this is now frequently employed in the turbine industry, especially to put down inexpensive corrosion protective layers on top of a pre-existing substrate. So, you will see an interesting transition. If you look at a turbine blade, it looks like this, and you cross section it, the bottommost surface will simply look like a steel, the topmost surface will look like what is known as a superalloy, which has the most enhanced corrosion protection properties, and in between you will see a transition zone where the properties of the substrate will slowly change from the low cost steel properties to the high cost superalloy properties. Another application of CVD coatings is on top of polymers. There are frequently applications where the substrate has to be a polymer, but the surface has to have enhanced properties beyond what a polymer can give. Typically these are used in biomedical type of medical devices, especially medical inserts that go into the human body. For various reasons these inserts have to be made of a chemically inert material like a plastic, but it must have sufficient surface resistance to things like chemical reactions and also diffusion in and diffusion out. You do not want impurities in the plastic to come out and pollute the human system, and at the same time you do not want the plastic to be degraded too quickly by something that may be diffusing into it from the human body. So, that is one example, but the plastics are used in many demanding environments because of their lightweight characteristics. So, anytime you talk about propulsion, payload, space applications, rocket launch, if they could, they would make the entire rocket out of plastic, right, because it's the weight of the rocket is what you are constantly fighting when you are launching. So, plastics are a highly desirable material, and rubbers also. So, all classes of polymers are very desirable in terms of certain properties, but they do have this one issue that a plastic surface can easily wear. It can easily be abraded, can easily be eroded, cannot be corroded so much, but physical damage is quite possible. So, it certainly makes sense to put down a coating on a polymer, and it is very difficult to do because plastics by definition are low surface energy materials, and so adhesion tends to be poor if you put down a coating, and also the chemical reactivity is also not very strong. And so, conventional coating processes do not work very well, and even conventional CVD processes do not seem to work too well. It is very difficult to get a CVD film to bond onto polymers, and also you cannot use high temperatures because most plastics will degrade, most polymers will degrade at high temperatures. So, what would you suggest if you wanted to use a CVD process for coating polymers? What would be an appropriate process? Plasma enhanced CVD, because that can be done virtually at room temperature, and the plasma itself will have multiple uses. It will provide the energy to improve adhesion. Plasma can also energize the vapor phase molecules, plus it can actually, when you irradiate a low surface energy surface with plasma, you can increase its surface energy. So, you can take a polymer and increase its surface energy by exposing it to a polymer. You can almost make it behave like a metal in terms of surface energy characteristics. So, plasma CVD for coating of polymers, and this can be a variety of polymers. You can coat everything from polyethylene to polypropylene to polystyrene, nylon, PET, anything can be CVD coated, but you do have to do it in a PECVD reactor and not in a low pressure CVD reactor or a atmospheric pressure CVD reactor. The other benefit of plasma enhanced CVD is, in addition to coating substrate that are large continuous surfaces, you can even coat fibers. So, for example, textile fibers can be coated using the plasma enhanced CVD process, and that can sometimes be very important again when the textile has to have certain properties. For example, in many applications that involve electronic components, electrostatic discharge can kill the device. So, you have to provide a static dissipative kind of environment for manufacturing, and one of the places where static discharge can happen is the human body, particularly the clothes, because that is where static forces can build up. So, what they do is these garments, they actually put down some coating on the fibers that are used in these garments to improve the conductivity, and therefore make it difficult for static charge to build up. So, that is a classic example of where you take a polymer surface and you coat it with something and you change its conductive properties. And similarly, if somebody has to go into a very high temperature environment, you have to provide sufficient thermal barrier protection, and for that you need again these types of coating. So, you can coat fibers, you can coat fibrils, you can even coat nano fibers essentially by using plasma enhanced CVD as the coating process. So, there are some very interesting applications of CVD that are used in the coatings industry, ranging all the way from large surfaces on which you are putting down microns thick coating to micro or nano applications where you are putting down very, very thin coatings on very, very tiny surfaces. And the amazing thing is CVD as a process is sufficiently flexible to allow all these different types of coatings to be realized. Okay, so let us stop our discussion at this point. In this next class, I think we have kind of discussed most of the basics of CVD in terms of applications. The one aspect that we need to cover is the properties of CVD films and how you would evaluate them, but the next few lectures will primarily concentrate on the transport phenomena involved. But before we do that, I also want to look at a couple more examples of CVD. I mentioned in the very first class, I think, about non-conventional CVD process, for example, such as those that happen in tungsten filament lamps or in high temperature corrosive environments. So, we will also take a little bit of time to discuss those processes, and then we will begin to focus on the core of this course, which is the transport phenomena and the chemical engineering principles involved. Okay, any questions on what we have talked about today?
Sir, Teflon coating that is also comes under this type of category.
Well, I was actually talking about coating of Teflon with a metal. So, it is kind of the reverse process. Teflon coating on metal surface, I mean, you do not need CVD to do that. You know, it's basically there are other processes that are available. But when you are trying to coat a polymer with a metal, that's actually a lot more difficult, because you have to do it without damaging the polymer. And so, and sometimes you have to do that as well, because there are many Teflon devices, particularly again in biomedical applications, that require a metal coating. That is where CVD is helpful. Coating of metals with plastics is not that difficult to do. I mean, there are many different processes that can do it with less complexity than a CVD process. Yeah.
And for powders are used for we need to have a free flowing property for that powders, very 200 micron size powders. For that case, we also by CVD technique or
yeah, I mean, CVD has an advantage that it coats not only continuous surfaces, but it can also coat individual particles. So, essentially the surface energetics again will favor the formation of a film around each particle surface. And so, if you have powders and you want to coat them with a CVD film, it is actually in many ways it consumes less energy to do that than to coat a continuous surface, because a particle by definition is more reactive than as film. So, I think that should not be too hard. Okay, so I will see you at the next lecture then.